All right. Hello, everybody. Hello to the hundreds of people online, and welcome to this session. So this is what I'm going to talk about today in pictorial form. I set out with a simple task of trying to make a new geometry of a basic capacitor, and you'll get to judge at the end if I passed or failed. So this capacitor consists of a nickel metal foam bottom electrode that is perfectly and conformally coated with an ALD dielectric. That could be ALD Hafnia, ferroelectric, or antiferroelectric. At ARL, we also have proper ALD antiferroelectrics like lead hafnate. And then we need a counter electrode that can fill all those nooks and crannies. And the best idea that I had was to fill the whole thing with liquid metal. So some of the advantage of this is there's a bit of a disconnect between the ALD ferroelectrics and actually having substrates that are appropriate for pulsed power. It has low series resistance because all of my conductors are very large. It has high surface area because it's a foam. And as you can imagine, this mix between very macro scale and very nanoscale engineering is very challenging to fab. So the first half of my talk, I'll go through the fabrication process, the thin film metrology, and then we'll talk about more of the device-related metrics. Now, since we are all close colleagues here, I'll give you the true motivation, which is not what I'm going to put in the paper. I'll one day get motivated enough to write. You may know some of my previous work. I was all about pyroelectric energy conversion. And I had gotten a sample from our collaborators on Fraunhofer that was a very high surface area Hafnia ferroelectric that we were using for pyroelectric energy conversion. And the apparent, keep in mind that this is normalized by the surface area, not the total area. The apparent pyroelectric coefficient was monstrous. I mean, for a planar PCT, it's more like 200 or 300. And yet, if you benchmark our 3D ALD Hafnia against what else has been in literature, somehow this plot didn't make the paper. It was way down towards the bottom. And so this had me really wondering, how come we cannot take advantage of this huge amount of pyroelectric area that has been folded up into these deep trenches? And the reason is because we were losing the precious little power we were getting pyroelectrically in having low conductivity electrodes. So let's keep that in our mind and move towards energy storage applications. So this is kind of the ubiquitous set of plots you see for an ALD ferroelectric energy storage paper. You have the hysteresis loop, and the area behind the loop is equivalent to the energy storage density. And then you can calculate the ratio of these areas, gives you your density and your energy storage efficiency. But if you look at the literature on bulk pulsed power applications, everybody makes sure to include some actual ballistic discharge tests. And this is really hard to do with an ALD, a small capacitor. It's just has a little amount of capacitance, and it's hard to just set up that experiment. So this had me further thinking about how can we fix this electrode problem so we can get these amazing ALD ferroelectric properties that could be more realistically tested under the conditions that the bulk ones are. This is the last time I'm going to show that GIF of me. The other thing that I wanted to highlight here is that also the community doesn't talk about capacitance density enough. It's often energy storage density. And for a lot of these applications, like there's a great invited talk on power capacitors. Capacitance density is what lets you scale your whole device area down. So this was the motivation behind trying to come up with this new capacitor geometry. So going through abbreviated fabrication steps, start with an off-the-shelf nickel metal foam and carefully thread a ground wire to it. This is something I would do at home during COVID. And then carefully grow an atomic layer thin film on top, then infiltrate this foam with liquid metal and add your counter electrode. And then this is the step that maybe we never quite got to. So let's talk about the atomic layer coating itself, because that's where most of the challenges lie. The composition that we did was 6% alumina-doped Hafnia, and this is a composition that was developed with a student that Jacob Jones and I were co-advising. We kind of settled on this at ARL as our token energy storage composition. We grew films from 20 to 200 nanometers, but most of what we'll talk about is between 50 and 80 today. We did successfully anneal them, but most of what we tested was unannealed because we were scared about them cracking or having them touch any other surfaces. We tried a bunch of various growth temperatures, and this is something I want to talk about real quick. Our ALD chamber is built for wafers, and I'm trying to put metal foams in there. So it's got a slot that's about 1 centimeter tall, and I also can't let the foams touch the surface at any point during the process. So they all had to be carefully cantilevered above the surface. Now, heat comes from the bottom platen, and the foams are only touching right here. So we measured thermal gradients of 50 to 60 degrees from the top to the bottom of the foam. That made it challenging to have the whole foam sit inside the ALD process window. Still, it grew, and so we can see some TEM of some unannealed foams, and then we were able to anneal the foams, and you can see grains here, and then there's these 2 little peaks that correspond to the lumina hafnia. Now, here's a photograph of the interface between what a coated infiltrated foam looks like. And if you've never played with liquid metal, it is a crazy non-intuitive substance. It's very dense, and it has this crazy surface tension. So actually getting the liquid metal to want to get into this foam was a challenge in and of itself. We did a bunch of chemical treatments, and it turned out that just pushing it as hard as we could, we even centrifuged it, was the best way to get it to infiltrate the foam. Now, I spent about a year with nothing but shorted foams, which was incredibly fun and frustrating. And these substrates are really hard to do subsequent metrology on because there isn't a flat surface to be found. There's very low density. And it wasn't until some careful SEM inspection that I found something that looked like this. And as I mentioned in an earlier session, my thesis was on tribology. So a sliding wear track is something that I'm familiar with seeing. And as soon as I realized that that flexion was okay, but sliding absolutely destroyed our ALD coating, I was able to start testing these foams. So let's move on to some device characterization. Here's what one of the test setups looked like. So instead of having sharp, pointy, scratchy probe tips, I terminated the probes with liquid gallium, and then this is one of the test setups where you would have essentially a capacitor in series orientation going on here. And here is the polarization hysteresis that we measured from an annealed foam. It is in the ALD hafnia community considered anti-ferroelectric-like. I don't have any idea what my area was, but I set the dielectric constant to be correct. And so I added a star there. Now, this composition, we compared it, this was a wafer that was fabricated with the same composition. And also we have to have arguments about it, but there is some nonlinearity here. And so we felt like, okay, the material that we were getting when it wasn't shorted was at least something that was indicative of what we could get in our high quality 6-inch fab process. Now, if we wanted to infiltrate and test the foam, I had to develop a soft microfluidic liquid metal input strategy to try to get the liquid metal in there. I don't know why Nazanin thinks this is so funny. It was really arduous to get this to work, but so there are internal channels and wells that I micromolded, and then this is what an actual infiltrated foam looks like. This is why I used that computer generated picture. And this is what the test set up. So here's the pre-threaded ground wire, which is clamped and accessed over here. And then there's a wire that is sitting in a well of liquid metal, which has continuity with the rest of the foam, or with the rest of the liquid metal inside of it. So one of the arguments for this is that we have lower resistance. So it could actually be thought of as a pulse power substrate. And I don't know where my other legend piece went, but here's the foam impedance, and here is a film from that wafer of what you would a deep trench kind of pulse power configuration etched out of silicon. So that part works out pretty well. Now, one of the more creative possibilities for this is the opportunity for thermal regulation. So this is gallium, and gallium melts at 80 C, and it supercools a whole bunch. So you could melt the gallium, and then you'd have plenty of time to try to infiltrate it into the foam, and then it would solidify. And so this DSC measurement, you can see, has 60 joules per gram of heat absorption that takes place right around this transition. This was probably not pure gallium, it was an alloy, because I'm seeing them way off. So if you just do some hand-wavy back of the envelope calculations, a commercial pulse power capacitor is about 1 joule per gram. The gallium is 90% of the weight of an unpackaged capacitor. So if you had a 90% efficient energy storage process, you could have a bunch of discharges that would just walk the temperature up and then start getting absorbed in trying to change the phase of the liquid gallium. Now, I don't want everything to live, I don't want this work to just be a total fantasy. So I got some back of the envelope calculations of what this could cost. Commercial nickel foam comes in rolls. Here's the area. ALD dielectric, maybe someone can give me a better number than this. My local ALD guy told me that this is about what you could expect. And then gallium is about $100 per kilogram. So given the commercial area of the foams, if you don't do anything fancy to crush them partially or anything, you're on the order, I know I'm probably off by at least 2 orders of magnitude, but you're on the order of cents per microfarad. So if you want to talk about a regular capacitor, you can't be on the order of $10 or $100 per microfarad, or you just should stop what you're doing. So in conclusion, we made a new geometry of capacitor that takes advantage of ALD ferroelectrics. It has high energy density. It could have high power density because we showed low impedance. You could think of doing thermal regulation by melting the inner electrode or even flowing the inner electrode in a closed loop. I didn't show it here, but they are flexible. This is something that John keyed me in on, is that the thin films are much more flexible than you would expect. I didn't discuss it, but so the capacitance density here kind of sits between MLCCs and electrolytic capacitors, but these are ALD ferroelectric, so they are bipolar, which could be really helpful in some certain situations. And of course, I've always got my eye on energy conversion. Maybe you can flow hot and cold liquid through there and do something pyroelectric. As you can imagine, it was very hard to keep this from shorting. So, and dealing with liquid metal is also pain. It permanently stains anything that you get it on, so be careful there. With that said, does anyone want to try to take the baton and make a foam capacitor? And that's where I'll leave it. I'd like to thank again Dr. Alexis Payne and subsequently Jacob for their work on the initial stuff. Conversations with John and Sam, and then our deposition engineer at ARL was willing to help me try to break the door for the ALD machine as much as possible. That's it. Thank you.
Thank you for that talk.
Thank you.
A lot of questions. Great. Thank you. So the first part of it is not a question. The first is comment. Mm-hmm. And I really appreciate for you keeping it honest and real. Mm-hmm. And the ingenuity that went through this project, because clearly it came from a very good idea. And then you had to travel, troubleshoot a lot of different things that went into it. So I really appreciate that you kept it real for us rather than just saying, this is a fabulous thing and it will, solve the energy problems of the world.
Thanks.
The second part of it is beyond the liquid metal. How much is the effect of the thickness of the ALD, or is there anything you can do with changing the material or on the dielectric itself that you think is important here versus all of the around the problem that is going to make a difference? Because otherwise the answer is yes, and we can talk about it.
Yeah, I think the first thing that I'm missing is a clever and relatively quick turnaround way to inspect the center of the film, or of the foam. So we could take TEM samples as deep as we could fib and lift out, and we would see differences between the top and bottom of the film. But in the absence, it doesn't take much to have a short, and we kind of got over the scratching-based shorting issues. And now it's a mystery about what the next shorting issue may be. So I don't know. I would start with the metrology and then use that to inform the next part.
Hey.
Hey.
So since melting of gallium is a problem. Why use gallium? Why not use an alloy with a higher melting temperature? A couple of years ago, we published a paper with Michael Dickey's group on printing of gallium with copper nanoparticles, for example.
Yeah.
And then when it solidifies, it has a higher melting temperature. So is this a potential solution to the melting problem?
Well, okay. I think melting is a feature, not a problem. It is just generally hard to work with, but having the heat that's generated during the pulse power events melt the gallium. So I would say perfect. Select an alloy that is processable, but then in your application is going to take heat from the system at that critical temperature as it melts. So this is EGAN, I think, for most of this, but there's gallon stand, you can get room temperature, sub-room temperature. Don't want to mess with mercury. But yeah, there are some creative things to be done on the liquid metal side there.
Last question over here.
Thanks. Very nice talk. I enjoyed it a lot. How about using, instead of liquid metal, if you would just use ALD and deposit titanium nitride, let's say, another layer, would it be too resistive?
So yeah, we can do ALD platinum where we are. The problem is then you have to create a coax cable somewhere that has just that 20 nanometer, 200 nanometer dielectric separation. Certainly a possibility. You know, if you imagine the original kind of configuration, and so let's say this whole thing's coated and you just have one cable that's threaded coming here, and this is coated with ALD and coated with platinum. If you etch back the platinum this much and etch back the ALD this much, then you have 2 points on this wire, which we top and bottom electrode. It just seems scary and hard to try to accomplish that. And we couldn't, there wasn't like a etch chemistry that made it sound like it was a knockout solution, but you certainly could complete this by doing a top ALD coating as well, which maybe you'd like to try.
Thanks.
Any further questions should be taken over coffee.
Okay.
So let's thank the speaker and all the speakers of this session again.
Thank you.
I didn't want to sound like a complete dummy, but like all this
So I hope it didn't come out wrong. I was just enjoying myself. It's like you came up with a totally new cool different thing, and it's just like, oh, but I come up with this, but now I have so many other problems as well. That, yeah, the clock's gonna take all up to whatever else. But I think no, actually no. I think it's a very good idea. I think it's just to come up to the details of how to solve the engineering around it, rather than the idea itself. The idea is good. How to it reminds me of the first time that we are presented and worked with the two-photon lithography printed metal structures. Yeah. And the first thing was, oh, we should do this in pencils and Ferroelectrics and hold them. And I got stuck at the electrodes. Right. Yeah. And then you were talking about